All right. Prop 20 says, in any triangle, two sides taken together in any manner are greater than the remaining one. So it's a pretty straightforward claim. It's just saying take two sides, take any triangle, take two sides, add them together. That sum is going to be larger than the third remaining side. So this is our old friend, the cornerstone of analysis, the triangle inequality. But we're going to prove it geometrically. Okie dokie. And just kind of at the outset, I'll state that there really are like three sort of relationships in this statement that would need to be proved. For instance, we would need to prove that AB plus BC is longer than AC. We need to prove that BC plus AC is longer than AB. And we need to prove that AC plus AB is longer than BC. I think I got all three of those right. It's kind of early in the morning and I haven't drinking enough coffee. So in any case, but we can do this as a without loss of generality proof. So we're going to go through it for two relationships, for one of those relationship, and then we'll just say, yeah, the same argument applies across the board. Okay, so how do we do it? Well, we're going to start off, and we're going to extend BA to a point D such that AD is equal in length to AC. So let me start there. Let's see, do I want to make the full circle? What the heck, why not? Let's see how it looks, see how it comes out. Alright, there's our circle. And I feel that this probably should be justified, like that we can do this. It's not justified in my text. I believe that it's proposition 3, the one that says that we can, I mean, on the one hand, it's postulate 2, saying that we can extend this line, and then proposition 3 that says that we can cut off on that extended line a segment equal to AC. So here's our point D. And we've constructed proof. So extend AB to D such that AD is equal to AC. And again, this is not, maybe I shouldn't write on here since I don't know for sure. I'm pretty sure it's proposition 3 that allows us to do that as postulate 2 in proposition 3, but it's not justified in here. It's just sort of stated. So, all right, well, if that's the case, if AD is equal to AC, that means that ACD, this triangle, is isosceles. And proposition 5 tells us that the angles at the base of an isosceles triangle are equal. So, then, angle ADC is equal to angle ACD, and that was by prop 5. All right. And as usual, Euclid just kind of makes this next statement, which is fairly obvious given the diagram, but I think that there should be some justification in there, so I'll write out what Euclid wrote. He said, therefore, angle BCD is greater than angle ADC. So this Euclid just claims this, and he justifies it. He says this is common notion 5, common notion 5 that gives us this fact. I would like to justify it a little bit more. I think that it's helpful. I mean, it is fairly obvious, but I think it's helpful to still justify it. And maybe if you're kind of like new to proofs, this might be a good spot to just take half of a second and justify this claim. Why do we say that angle BCD is greater than angle ADC? Well, I claim it's because angle BCD is the sum of these two angles. It's because angle BCD is equal to angle BCA plus angle ACD. And we just concluded a moment ago that angle ACD is equal to angle ADC. So this is equal to angle BCA plus angle ADC. And here's kind of like the unspoken piece that sort of we would need in order for this to be true, is that angle BCA is positive. The Greeks didn't, they weren't worried about negative numbers. They weren't worried about negative angles. So yeah, if you have two things being added together, that sum is greater than the parts. So not equal to, but this is strictly greater than angle ADC. That's a greater than symbol. And this was the claim that we just got, that angle BCD is greater than angle ADC. So there's kind of like the intermediary steps for proving that this is true. Again, fairly obvious if you just look at the diagram, but today we say a picture is not a proof. So, but for the Greeks that was enough, that was fairly obvious. Okie dokie. So angle BCD is greater than angle ADC up here. Okie dokie, what's next? Right, so then next he says, well, if you look at the triangle, like this large triangle that we created, triangle BDC, DCB is what he says it. He says, and since DCB is a triangle having the angle BCD greater than the angle BDC, and the greater angle is subtended by the greater side, therefore DB is greater than BC. So, I might say, in triangle DCB, in triangle DCB, since angle BCD is greater than, is a triangle having angle BCD, yeah, BCD greater than BDC. So BCD is greater than angle BDC. So let me see, what are we talking about here? BCD is greater than the angle BDC. Yeah, and that just follows because the angle BDC is the same as the angle ADC. So we just proved this essentially. Yeah, if you wanted to, you could just put a little equals BDC equals ADC to justify that a little bit further. But since this is the case, the greater angle is subtended by the greater side, so since this is true, it follows that side DB is greater than side BC. And that was from proposition 19. So again, just looking at the diagram, so since BCD is greater than BDC, it follows that the side that is opposite BCD, which is BD or DB, is greater than the side that is opposite BDC, which is BC. And can you see why this kind of actually proves what we needed it to prove? The reason is because look at what DB is made up of. So DB is made up of DA plus AB, but DA is equal to AC. So DB is really the same as AC plus AB, and we just said that that's greater than BC. So that's what we needed. Let's see, what does Euclid say? Right, but he says, but DA is equal to AC. And he says, therefore, BAAC are greater than BC. So I might say, but DB is equal to DA plus AB. And by construction, DA is equal to AC. So the result follows. We have that DB, which is equal to AC plus AB is greater than BC. And this is what we needed to prove. AC plus AB is larger than BC. Let's see, a similar argument. Proves, maybe I'll say, proves the proposition for the other sides as well. It's lazy, but I think it gets the points across. That's it. QED. Therefore, etc.